school, guys. And it's currently school year or SY 2022 to 2023. Um, and yeah, again, I'm your instructor or your lecturer for this course, Professor Femi Suk. And yeah, we're gonna begin discussing our position theory course. And before we begin the course, um, it's important that I tell you guys first, or give you guys a good, you know, reviewer before we start. So, let's see if it might work. Okay, this one. Push that one. So that. Okay, this one too. See the one that I just bought. Okay, so in this lecture, I'm just gonna be discussing the important concepts, or at least the most basic concepts you guys need to know before you start this course. Um, I think I already mentioned in the uh, in the introduction video that you may need some. Well, of course, you guys need to know a little bit of math to know to continue with this course. I'm sorry if I'm pushing a little. I'm sorry, really, if I'm pushing you guys to actually learn math just for like these joke lectures. I know these lectures are supposed to be jokes taken to the extreme, but ultimately, if you guys want to understand the abstractions and the things that I say or do in these lectures, or lecture about, you guys really need to put in a little effort in order to understand. It's really something you guys need to do if you enroll in LOSC. So we take things seriously here with a hint of jokery in it. So, right. So in this video, or in this lecture, I'm gonna be, teaching a little bit of set theory, a little bit of topology, and a little bit of linear algebra, and vector calculus. And so in this video, I'm assuming you guys already know basic ZFC, or Zermelo-Fraenkel set theory, and calculus 1 and 2. So the prerequisites to vector calculus, I'm expecting you guys to already know. So stuff like partial derivatives and stuff like that. We're just going to be discussing about curl when we get to the vector calculus part. We're just going to be discussing about curl and divergence and vector fields. That's all we're going to be discussing. And obviously, as a prerequisite to that, I need you guys to know about linear algebra in general. But we're just going to, for those who needs a little recap, this video is for you. Otherwise, if you guys already know these three subjects, you guys can carry on with the course. So the first and most important thing that you guys need to know is the set. So what is a set? What is a set? Now, Gord Cantor made a rigorous definition for what a set is by laying down two fundamental assumptions or axioms. The first one is comprehension and extensionality. So what comprehension states is that for a given set X, say for a given set X, there is a condition, or given set X, and then there's a condition on X, which I'll call P on X, P of X. There should be a corresponding set Y that satisfies P of X. So for a X that satisfies a P of X, there should be a Y that is a representation of X, or a subset of X that satisfies this. And so the second one is extensionality, and that basically asserts that if Y exists, a subset A of Y, so Y exists, implies that a subset A of Y exists. So yeah, if the subsets, likewise, if the subsets, or if a subset A subset Y exists, that that means that y, capital Y exists. Alright. But the problem here is that when George Cantor laid down these two very nice axioms, he was able to prove certain axioms, or he was able to, well, talk about infinity and stuff like that, and prove some theorems concerning infinity and, infinite sets. But the problem was when Bertrand Russell came into the scene of mathematics or logic, he constructed a paradox, or he considered the case that for an x inside x is not inside x. So what he wanted was an element inside the set to not be inside that set. But this implies that there is a set x that is part of x if and only if that x is not part of x, which is a contradiction. So I'll write the Halmos here. So it's a contradiction here, and this is what is known as Russell's paradox. I don't know if you guys can see it, hopefully. So this is called Russell's paradox, and it destroyed whatever work Cantor did. Now, Ernst Zermelo and Richard Dedekind laid down, and other people laid down more fundamental or more axioms, basically, that allowed us to basically model mathematical logic without running into paradoxes such as Russell's paradox. And this is where ZFC was formed. ZFC, which stands for Zermelo, Frankel. So Frankel and Zermelo did this primarily, and then Dedekind just basically contributed to it. Set theory plus the axiom of choice. I don't know if you guys can see this. Axiom of choice. Now, the first time I encountered axiom choice was reading a paper about the Banach-Tarski paradox. And you guys already know that if you guys watch my channel, because I talked about it a lot, especially in femboy theory, when I proved certain things like a femboy is independent, or a femboy set is independent from the definition of being gay. I required the use of the Banach-Tarski paradox, or the strong version of the Banach-Tarski paradox, and that paradox required the axiom of choice. And so the axiom of choice is a rather very controversial axiom in the foundations of mathematics. And it states roughly that given an arbitrary choice, amount of choices, there is a function that assigns precisely one option for each choice. So this is the axiom of choice. And so, in an example, suppose I have the option between these four, the option. Suppose I have the option to choose which marker to use among these four markers, right? So the axiom of choice tells me that I can think, or there is precisely one choice per these guys. So I cannot choose two from this one. So there's only one option for this option. And there's a function that tells me, or there's something in my mind that tells me that there is merely one per option. One option per choice. One choice per option. This was used by Banach and Tarski to construct their paradox, which basically states that given an open ball, not really an open ball, but a unit ball of radius 1, well, of course, a unit ball is a unit ball, and the unit means 1, and it's a ball with a radius of 1. without the center. So I'll call this B cubed. So this is a sphere. This is a sphere. Minus the origin. Now this is our notation for reducing or something that's not part. So we remove it. I'll rewrite it out here. B cubed without the center. That's O. That's the origin or 0. So we remove 0 from this, and then we also remove some troublesome points. D squared or D. And then from there, we also remove the poles. We remove the poles. We remove stuff that are fixed. So if we rotate it, they stay the same place, but we remove those. So we remove the center, of course, and then those other points, which is the set D. And from there, we can say that this ball, this unit ball, is equally decomposable with 2 copies of itself. So we can break it apart into pieces and then reconstruct those pieces or put those pieces back together to get 2 copies of this thing. And that was done through the axiom of choice. And that's why it was so controversial, because an extended version of the Banach-Tarski paradox tells us that we can end up with a small thing that's the size of a pea. So we can start with a pea and then end up with something as large as the sun, just by cutting it up and then rearranging it. By cutting apart and rearranging this small circle, we end up with this big circle, according to the Banach-Tarski paradox. And obviously, that doesn't make sense, because it goes against the second law of thermodynamics, or the conservation of energy. So yeah, that's why it's called a paradox, because it conflicts with what really happens in real life. Obviously, we cannot rearrange something and then come up with 2 things. But anyway, that's something for a different video. I was just discussing about why the axiom of choice was a very controversial thing. Now, moving on from set theory, I ought to discuss some topology, because it's a good way to rigorously define our regions. So so we're gonna be working with spaces most of the time, and when we start talking about spaces, we want to talk about the topological spaces as well, because topological spaces give us a rigorous definition for various things like compactness, connectedness, and stuff like that. So if we want to rigorously define a metric over something or some space, or if we want to start assigning people to labels such as bottom, top, and switch, the 3 main gender position states, we need a rigorous way of defining what exactly our space is, and that is done through topology. So now, a bit of topology. Happy face. I don't know if you guys can see that. It's a bit of topology. Happy face. Now, what exactly is a topology? It's not just the name of the subject itself or the branch of mathematics, but it's an actual mathematical construction or entity. So given a set X, so let X be a set. So it can be any combination or collection of objects you can think of, like 4, 1, 2, 3, 4, the integers, the rational numbers, the real numbers, those are sets. So let X be a set. A topology on X, which we will denote as T of X. Let's use math calc. T of X is a collection of subsets from X, and it's composed of X and the empty set. Tx is composed of X and the empty set, which we'll denote by Varnock, or the circle with a line on it. I don't know if you guys can see it. So that's the definition of a topology on a set X. And so things like the real numbers or the things that we do ever since basically elementary, ever since we started learning about math, that's all done within what are called as topological spaces. Topological spaces. Now, you guys know already that by the definition of the Greek words, so topology is derived from two Greek words, topos, and of course the common suffix for studying things, ology, so the study of location. So that's how I like to think about what topology means in the sense of the name of the subject. So now a very important concept of topology is called the topological space. And a topological space is a structure, a mathematical structure. And what are mathematical structures? Mathematical structures are basically things that we do equations and stuff on. So you guys know about the quadratic equation. So x 1, 2 is equal to b minus b plus minus the square root of b squared minus 4ac over 2a. You guys know this from your high school. But where does all this happen anyway? Where does this all happen? Think of sets or mathematical structures as locations. Like literally, in real life, locations, structures, buildings are structures, bridges are structures, houses are structures. Now in mathematics, a mathematical structure is where things happen. So they are sets with operations. So basically the place where it happens. So we're allowed to do this. We do this in this place or this collection of objects, which are sets. So where does this happen? This happens mostly in the real numbers. So Rn equipped with, we have these various operations. So we have plus minus, we have multiplication for AC, we have division, which is just multiplying by inverse. So we don't need that. We don't need to list. We don't need to list this. No, we don't need to. So that we have division, and then yeah, I think that's it. So this is the mathematical structure that we're doing. So we have a set, and then we have two operations you can do on the elements of this set, and this is a mathematical structure. Now, topological spaces is a specific type of mathematical structure. It's a location where things can happen. And a topological space is basically a set X equipped with its topology. So, mathcal X. This construction, we call these as constructions, is a topological space. A set equipped with its own topology. Now I like to call this topology the discrete topology on X because it's more interesting. If we have an indiscrete topology, it's just it's a trivial topology and it's boring. But I guess that's something you guys can find out in actually studying topology. And so what's an example of a topological space? So an example of a topological space is Rn, of course. We have Rn equipped with B of Rn. Where B of Rn is the box topology. You guys can search that up. Topology. Box topology on Rn. Where Rn is just the real numbers multiplied with itself all over again. So when we say a number set or a set multiplied by itself, so x to the n is basically x by x by x by dot 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 by x, and this is done n times. So in the case of Rn, the majority of mathematics that we deal with is actually happening in R2. So ever since our elementary days, like adding numbers, subtracting numbers, they all happen within R2. And that's basically all orders, all pairs of numbers, x, y, that are inside R. So x, y such that x, y are in R. And you guys know R the real numbers. So basically this R2 is a culmination or a combination. Not really a combination but a pairing. So I'll list down R2 here. You can think of it as axes, two axes. This is R, this is R. And we think of this as the x-axis most of the time. So during your high school days, you're taught that this is the y-axis and this is the x-axis. Where in the x-axis, given a function, the x-axis determines the y value. So we have a function here, you guys know those functions. We have x squared, we have the sine, we have the cosine, and you guys know that, tangent, etc., etc. But what the teachers don't tell you is where it all happens, where all of these things come from. And it all comes from R multiplied by itself. So this can be what we think. And then so R3, you guys can think about it. This is already R by R. And now R3 you guys can think of as three-dimensional space. So R by R by R. And R3 now is defined as the triplet of points x, y, z, such that x, y, and z are elements of R. And that could be think of as a third axis running perpendicular to both of these guys. And yeah, this is another R here. And then we have, this time, instead of 2 points, we have 3 points with depth. There. So we have x, y, and z. That's R3. And then R4 is four-dimensional space. Or Minkowski space. Minkowski space. R4, equipped with its topology. I'll name it the P R4. Minkowski space. Now, when I get more in depth in position theory, we're gonna run into a bunch of topological concepts, such as the separation axioms, compactness, connectedness. It really depends. Our curriculum is really dynamic, so it's constantly changing because of how modern mathematics is. So much time? It's 22 minutes so far. So that's basically the topology right now that we want. So spaces, and so yeah, we're mostly gonna be talking about these guys. So we want to assign a set of characteristics and a set of sexualities or sexual preferences or sexual orientations. So if we denote O to be the set of all preferences and presentation, so B, mathcal B, to be set of all preferences for looks, so gender identity, we're gonna take these guys or take their product and then equip it with their topology. And then this is the space that we're mostly going to be working with, which is called we don't really have a name for it. It's mostly just a projective space. It's a topological space either way. It's a space wherein each of these guys describe. So we have a certain O, small O, from big O. And we have a certain rho from mathcal P. And so this time we want 2 points. So we have 2 points, 2 elements or 2 coordinates, or rather 1 pair of coordinates to describe a person, right? Or given that though, we have certain regions of this topological space that describe the person and yada yada yada. This is basically how we're gonna apply it, but it'll be in the first lecture. We're getting to know the ropes when it comes to these things. So topology is a very important topic, especially when we start talking about vector spaces. Now, vector spaces are not entirely topological spaces. There's a specific name for that, which is a topological vector space, which is a vector space V equipped with its topology. That's a topological vector space. But in general, a vector space is just a set of vectors. That's all, to be honest. So given a bunch of vectors, which is so conveniently expressed as arrows, oh thank God. Thank God they're expressed in this way. This is how physicists think of them. Computer science students think of them as an array of numbers, so lists of numbers. ABC is a vector V. Now mathematicians, on the other hand, think that vectors are things that we can add, abstract objects that are part of what are known as vector spaces. So we're now dabbling into vector algebra, linear algebra. So now we're in the linear algebra part of this lecture. So most important concept, vector spaces. Because our product a while ago that I showed you that we're gonna use O by MathCal P, this over here, well, this set basically is already a vector space. This is a vector space. This would be a vector space. Unless you want to talk about it as like a Euclidean space. But since we're using vectors here, it's more neat to express things as vector quantities after all. We're going to be saying that this product is a vector space. So vector spaces are sets of vectors. So sets whose elements are vectors. Now, if you want to think like a mathematician, it's best to start abstracting things. You start thinking of things in the abstract sense. They're not physical things, but they're abstract things that have no form. But they have an interpretation which people think is the form. So physicists think of them as arrows in space that have a direction and a magnitude. And computer science students think of them as ordered lists of stuff, right? But us mathematicians, we think of vectors as abstract objects that we can add, subtract, multiply, divide. And these are elements of a vector space. That's what vectors are. Now, a very, 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 very important topic in modern mathematics. And I mean very, very important. Like this is in every corner of mathematics you guys can encounter. Engineering, physics, whatever, this is there. Well, almost. And that, my friends, or my students, is the matrix. Now you guys probably heard about this back in your high school days as rectangular arrays of numbers. Rectangular arrays of numbers. But you guys are only told in high school that these guys are only rectangular arrays themselves. ABC, DEF, GHI. That's all you guys are told. This is a matrix. They are arrays of numbers. That's it. You learned Kramer's rule. They help us solve systems of equations, yada yada yada, whatever your teacher tells you. But what they don't tell you in school or back in high school that you start to learn when you really start getting into linear algebra is that these matrices are a beautiful way of encoding change to a system. So suppose I have a vector space. So I have a vector space over here, and we want to show it as a grid so we know what points look like. I'm going to use this blue. Okay, so we have a grid that tells us the spacing. 1, 2, 3, 4, 1, 2, 3, 4. So we have a grid that tells us the spacing of the vectors. Here's a vector over here, which is 1, 2, 1, 2, 2, 2. We have these things called basis vectors, and these basis vectors are I hat and j hat. They are of precisely unit 1, and they determine what your system looks like. So the system over here is what it looks like because of the basis vectors. And the most basic basis vectors, or the simplest one, is I hat and j hat. I hat and j hat. And I'm gonna use head notation to denote what these guys look like, or what vectors look like. I don't know if you guys can see it. Okay, so I hat and j hat all have a unit of 1. I hat runs to the right and j hat moves upwards. So this goes 1 in the x direction, and it doesn't move up. And then j is just the opposite. These guys tells us what our system looks like. And now you guys are probably thinking, what does all of this have to do with matrices? Where the heck are the matrices? What do they have to do with this thing, this concept? Well, matrices are what we call as linear transformations. And there's a video that 3 Blue 1 Brown has already made about this, explaining exactly what they do. But I want to recall it here. What linear transforms are, denote a linear transform as an L. They are functions. They are maps that take one vector space and then spit out another vector space. They spit out another vector space given one vector space. And this second vector space is what this vector space looks like when we apply this on every single vector inside this vector space. So suppose V1 is composed of vectors A, B, C, D. Suppose that this vector space is composed of these guys. A linear transform on this transforms each of the vectors. L of A, L of B, L of C, and L of D. What it changes every vector in this vector space. And because every vector is changed, that means the grid that I drew a while ago is also moved around. So they're moved, stretched, squished, or what. And these linear transformations, which are mapped, L maps V1 onto, I like to throw the fancy arrows, onto V1 itself. Mostly this is the case here. So it maps a vector space onto itself, but in a different way. So it changes the vectors of it changes the coordinates of every vector you know in that vector space to another one. And it does that by changing the basis vectors. And it's because of this one simple and intuitive thing on how we express vectors. So you guys know how a vector is expressed via a 1 column, 2 row, 3 row, n row case. So this is a 2-dimensional vector, which I would say AB. The neat thing about expressing these guys is we can express them in terms of the unit, in terms of the basis vectors. We know that I hat is expressed as 1, 0, and j hat as 0, 1. So we can express this AB as a sum between these two things. So I'll call this vector V. So we can express vector V as A times I hat plus B times j hat. And that's the same thing, because A times, I'll use the rectangular notation here, 1, 0 plus B, 0, 1, and then so this becomes A 0 plus 0B, and that gives us the same thing here, AB. So that's true. No need to doubt this. It's true, and it works out. Just can't work out the calculations for yourself. You can try this for any arbitrary vector V. But the thing is, when we start changing things, or when we apply linear transform on a vector space, this is what happens. It changes the vectors and it switches the basis. What it does is switches the basis so that every vector is changed too, right? Since I told you guys that we can express every vector in terms of the basis vectors, just one change to the basis vectors already changes all of the vectors that we know in there. And this change is encoded in a matrix, as I said a while ago. This is a two-dimensional matrix of rank 2, and it has n 2 columns, 2 rows. So this is the columns, this is the rows. And these guys change the coordinates of I hat and j hat. So the new coordinate for I hat now, with this change, is AC, and the new coordinate for j hat is BD. So it changes it now. It changes these so that every single vector you know that can be expressed in terms of these two basis vectors, which is basically all of the vectors, except the zero vector, because zero vectors is 0, is changed. All of them is changed. Everything is changed. Everything is shifted. So think about that. Think about that grid that I wrote a while ago, or I drew a while ago. Think of it moving around, stretching, squishing. But there is an important constraint when we talk about these things, and that is called linearity. That's why it's called a linear transformation. That's because every single line stays straight and they don't bend. So suppose this is this is a line. This one collection of vectors in our thing a while ago, in our system a while ago. It cannot do this to the line. It cannot turn the line into this thing here. That's what a linear transform cannot do. It cannot bend a line. It can only stretch, squish, or rotate it. That's what linear means. And they all stay evenly spaced. So over here, if I draw these two lines with transverses in them, or write a square here and another square, and then assume that these squares have the same thing, and we apply the linear transform to make them all twice as big. So now we have this. But the thing is, the spacing between each of these vectors are stay the same. These are still squares. They don't become rectangles, they don't become triangles, they stay squares. So the spacing is preserved between these guys. That's why they're called linear transformations. Alright, and that's practically all you guys need to know about linear algebra. Now, a bit of quantum mechanics and notation, because when we express T, the bottom, and the switch, we actually express that in terms of vector quantities, and we denote them via this weird line and sort of angle type thing. And this is called Ket notation, bracket notation. And this was introduced by Dirac, I think. Not sure actually, but this bracket notation, and it's a very important thing in quantum mechanics because it makes things more compact and it's less tedious. And the thing is, the weird thing about position theory is that these guys, the top, the bottom, and the switch, are not precisely vector quantities themselves, but they're rather part of some space. So they're part of some space that our mu bar maps a certain O. O by P onto. So it maps this O by P to S. So a certain person in this space is mapped onto either one of these guys. And it's not really a vector themselves, but they're rather some abstract measure or metric. But the thing is, that's that. It's a compact way of expressing vectors. And what's neat is that it's the way physicists encode the wave function, which is psi, is equal to the spin up state, which is j hat, spin up state by alpha plus the spin side state, which is I hat, plus pi beta. And this is what I talked about in femboyology. And of course, alpha and beta are elements of the complex numbers. These are complex valued functions, and we encode them via these things. This is actually just j hat, this is I hat. Spin up and spin side states. So vector quantities are a good way of denoting states or encoding states, and this is why we want to use them in position theory, because a position is a state of a person. So if you are top, your state is that you're a top. If you're bottom, your state is that you're bottom. If you're switch, your state is that you're a switch. Now the last thing is vector calculus. Now I'm expecting you guys to understand what d over dx is. This is a derivative, slope, inclination with respect to x. This is d by y. But you guys know this. I'm gonna use flammable mass notation, or just Euler's notation, which is just a big del, and then we have our variable we're differentiating with respect to, and then our function, our given function. With f is x, y, and z. This is this is f, or rather we can write as t. So it's partial derivative notation. Now you guys need to know about what a Dell operator is. So a Dell operator is basically, it's a vector valued function. So it's a vector function, something like that. But it's sort of a generalized thing. It's an abstract function or mapping that asks us to take certain derivatives. And it's defined via this upside down triangle, which we call as nabla. And nabla is equivalent to d over dx, comma, d over d, or I'll just write via what I said a while ago, dx, dy, and dz. And what we mostly do with these things is we multiply them by a certain function, which is mostly the dot product or the cross product. So I'm kind of expecting you guys to know what the cross product and the dot product is. Dot product is basically just, well, by f, we just certainly just take the sum of the products between f and these entities. So this is dxf plus dyf plus dzf. And this is the Laplacian. Very neat, isn't it? This is the notation for a Laplacian. If we say a dot product, we can just put an f beside it as if denoting multiplication. But the thing is, this dot is not the same as this x operation here, because this is called the cross product of f, and it's asking us to take the Jacobian matrix with respect, or multiply, take the Jacobian matrix of f, but not really the Jacobian, but rather it's a specific type. So this dot product by f is defined as the determinant of, if I remember correctly, I, j, and k, where these are basis vectors, d dx, d dy, d dz, and then are certain parts of the function. It can actually just be f1, f2, f3. Take the determinant of this, and then you get the cross product of this function. Now this is very important because when we start talking about curl and divergence, this is a good way to encode what they are. So let's start with vector fields. Now you guys are probably thinking, oh, what's the difference between a vector field and a vector space? The thing is, vector fields, yes, they're sort of like vector spaces, but they're more of on the physical side. So I must say first that a vector space is not the same as a vector field. These two are not the same things. Because a vector field is the notion or the concept of assigning every point on a space with a corresponding vector. So suppose I have this system over here, R by R cross R. And then we have certain points. We're going to assign each point with a corresponding vector, and these vectors go in what direction a function dictates. So let's assign vectors to every point, These are just random. I don't think anyone can actually model this vector field in in actual stuff or actual softwares. It's just a random thing. But if we assign every point on a certain system with vectors, that's a vector field. And vector fields are encoded, or we can draw a vector field or make a vector field by multiplying a function, a multivariable function, with I hat and j hat. So a vector field f, which I'll denote by boldface f or blackboard bold f, is equivalent to q1 by I hat plus q2 by j hat. Wherein q1 is some two-dimensional function f of x, y, and then q2 is another function f of x, y. So what this is to say, it's a mapping. F really is a mapping between a sort of a combination. So it's a product between products. So R cross R plus R cross R. So R cross R by R cross R onto, well, F onto R. So R cross R by R cross R onto, I guess it's some R2. Some, yeah, we're given R cross R. So that's what vector field does. So it's a function of functions, basically. And it's a bit wonky, but once you guys get to know it, and a more compact form of writing this is F is equal to Q1, Q2, XY, X. Where, of course, we want that Q1 is not equal to Q2. Otherwise, we get a very simple and not really interesting vector field. And, alright, there are two very important properties of a vector field that we want to consider. And these two are curl and divergence. We're 47 minutes now. Curl and divergence. Now curl is basically just given a point on our vector field, how much or what's the measure of how the vectors around it curl around it. So given a point, we want to know how much vectors go around it. If we have a positive curl around this point, that means it's moving in a clockwise direction. And if we have negative curl, it goes in this direction. And curl of the vector function boldface f is equal to the cross product between f and this, which is the determinant of this matrix. We have dx, dy, z, this time q1, q2, we're in, well, of course, now we have a three-dimensional function here. And actually, most vector fields that are 2D are still expressed via three dimensions, or three bases, and three functions over here. And then, of course, yeah, it tells us the rate of how vectors rotate around it, or go around a certain point. Now, divergence, as stated by the name, is how much vectors go away from a point. So given a point, we want to know how points go away from it, or how vectors go away or point away from it. When we have positive divergence, that means vectors mostly point away from that point. When we say negative divergence or convergence, that means points go into the point. And when we model stuff like fluids, like water, via vector fields, we say that it has no holes. It's continuous and therefore has no divergence. It's actually an arbitrary fluid. It has some very dirty. So, yeah, I think that's actually it for this building intuition lecture. I hope you guys were able to see that. This is all done in one go and in one shot. So, yeah, the next the next thing is that we're gonna start the lecture. We're gonna start the course. And it all begins with O by P. Of course, maybe equipped with its topology. There. And of course, our three main position states: top, bottom, switch. Top, bottom, switch. Very important. Very important. And so that's it for this lecture. A bit wheezy, but to continue. That's it for this lecture, and I suppose I'll see you guys in the actual first lecture.